Good afternoon, ladies and gentlemen. Welcome. Thank you very much for joining this pair distinguished lectures. I'm C.S. Poon, the Director of Research Center for Resources Engineering towards Carbon Neutrality under PAIR. I'm delighted to introduce our distinguished speaker today, Professor Banthia, a renowned expert in structural material engineering from the University of British Columbia, Canada, where he holds the title as the University Killam Professor, Distinguished University Scholar, and Senior Canada Research Chair. Professor Banthia is widely credited for his research in the area of carbon neutral concrete infrastructure, resilient concrete structures, as well as sensor-based infrastructure management. His significant innovation include sustainable coating and repair material to address the problem of corrosion in utility infrastructure. Professor Banthia has developed new coating material that offer superior resistance compared to conventional cement-based coating. He has also developed carbon-neutral concrete coating made from recycled materials, specially designed for repairing old and deteriorated sewer pipes. His other research achievements include a novel method for repairing damaged structures. This technique, called spray fiber reinforced polymer technology, involves spraying polymer and shot randomly distributed fiber on the surface of concrete. He has been proven to be the strongest and least costly method of bridge deck repair. Professor Banthia's dedication to advancing the safety and sustainability of civil structures goes beyond research. He also leads a consortium called IC Impacts, which stands for India-Canada Center for Innovative Multidiscipline Partnerships to Accelerate Community Transformation and Sustainability. This platform forged multi-sector engagement between Canada and India to solve urgent challenges in water, health, infrastructure, and food. Professor Banthia's work have earned extensive media coverage and multi-academic and community honors. He is a fellow of prestigious society including the Canadian Academy of Engineering, the Indian National Academy of Engineering, and the Royal Society of Canada. Without further ado, ladies and gentlemen, please join me in welcoming Professor Banthia.
Thank you very much, Professor Poon, and wonderful to see you, Professor Teng. Great to be here today. I'm delighted to be part of this, and thank you for the invitation to this PAIR fellowship to give a talk. Again, the title of the talk is Towards Carbon Neutral Cities, Sensors and Cyber Physical Networks for Green Infrastructure. So we'll talk about basically sensors, but the whole purpose of these sensors is to create green cities and to understand how structural management can occur as a result of using sensor data, particularly through machine learning and AI. Greetings from University of British Columbia. I mean, your campus resembles quite a bit UBC as well, actually, which is nice to have the ocean so close to the campus, which is lovely. So I'm pleased to be here. So the outline is, I'll talk about the carbon emission in the built environment. And as you know, we are the big elephant in the room in terms of our built environment, how much carbon we generate as a result of our construction activities. So we'll talk about the carbon emission in the built environment. Then I'll move over to digital economy, monitored smart city, and green city. As you know, there is a digital revolution going on there. You know, every time you hail a cab using Uber or some Didi or whatever app you use, you're using essentially a digital platform. When you book a room on Airbnb, you're using a digital spine, which is allowing you to do a lot of things actually online, basically. Construction, unfortunately, tends to be lagging behind in this sense, and we really need to come up with better ways of actually using the digitalization that is happening. And I believe the digitalization in this particular case will help us also reduce our carbon emissions, because that's really where I believe a lot of the possibilities are. So I want to talk about operational monitoring, comfort, and carbon reduction, the heating, lighting, HVAC, which actually is a huge source of carbon emission, unfortunately. Now we talk about the structural health monitoring for safety and carbon reduction. And then we'll deal with resilience monitoring for disaster prevention. And I'm sure Hong Kong is no stranger to disasters. So we'll also talk about how we can make our structures more disaster resilience. And then we'll have a closure. So the total GHG by country is rising. As you know, we actually are recording no less. I mean, we're talking about this 1.5-degree rise, but we have already actually gone to 2.3%, 3.23, 2.3 degrees already. So, this Paris Accord where we talked about this 1.5-degree increase, it didn't happen, unfortunately, and our emissions are absolutely still going up. And what we really suspect is that we continue as many coastal areas, and certainly Hong Kong also has current issues to deal with its coastal protection as well. But we expect that Vancouver will be underwater by 2100 if we continue to basically do things as we are doing. So I think this, this is just one symptom of the problem, is the rising sea levels. But there are, of course, other issues that we are dealing with as well. And I think we need to all collectively work towards what we do. Now, where are our emissions coming from? When you look at, the world generates about 80 gigatons of emissions now, 80 gigatons of GHG. About half of it, 51%, literally comes from our built environment. So you look at, the total emissions that we are creating basically comes from our built environment. Of that 51%, the building operations cost about, or are approximately responsible for about 28%. So, your maintenance, your building operations, your heating, vacuum, heating, HVAC, etc., they actually amount to about 28%. Now, of course, from concrete side, and Professor Poon is the expert in all of these carbon neutral concrete materials, you're looking at approximately the embedded energy in these building materials like concrete, steel, and aluminum is approximately 23%, and concrete alone is at 11.1%. So really, you're looking at a massive emission that is coming from our industry, which is basically construction and et cetera. Now, there's been a lot of work done on reducing the embedded carbon. So there's a lot of work. You look at sort of what we have been doing. We've been, on the cement, recycled tires and aggregate, water, because, concrete requires, I'm sort of focusing on concrete now. So you're basically looking at low carbon structures. You're looking at basically things which were, because water required is actually drinkable water. So treatment becomes an issue, which is extremely carbon intensive. Now you have, of course, the CO2 curing that has been also going on also in many parts of the world where you're sequestering CO2, all that we are generating. But if you're looking at now the life cycle carbon, that 28% that I was talking about, you need new methods. And what I want to discuss is basically these are the sort of the new methods we are looking at as resilience, which is through ultra high performance concrete, for example, so that you don't have to, rebuild the structure very rapidly because the structure will last much longer now. And what we are looking at now is basically sensors. And of course, there's strengthening as well. But today, I want to focus on sensors, how we can actually use the sensors to reduce our life cycle carbon in our structures. How can the sensors actually help us? And the whole idea is that how we can actually put these sensors in the structure with the ultimate aim of not just reducing carbon, but also improving its resilience in the long run. Now, we have been doing things, in fact, in a very traditional way in our industry. So if you look at the construction industry, and what you will notice is really we have, you have sort of these traditional areas where you have structures and materials and design, construction, project management. So we've been doing all these things as we have done for many, many more years before. What we are trying to introduce, I think, and this is really where we have been lagging behind, is putting really some cyber physical interface where we can locate some sensors, some ICT platforms, do a structural health monitoring, use AI. And what I believe is that if you bring this kind of cyber physical interface where you're putting sensors in a structure, etc., what you can do is you can get a lot better out of life cycle costing, asset management, decision making, deconstructibility, and of course, reducing the overall carbon that is coming from our industry itself. Now, the water guys, as Professor Poon just talked about, our center with India, IC Impacts, the water guys are extremely, extremely advanced in this area. So here is a typical ICT platform for water quality monitoring, which has got water sensors. So water sensors can detect basically any pathogen, the chemicals, the cryptosporidium, E. coli, and these sensors exist. What that means is if you have this sensor, which is actually detecting a specific pathogen or some kind of a chemical that can be fed into an ICT model, which means that through fluid dynamics or particularly understanding how the fluids will flow, you can detect basically how has this particular pathogen moved through the system, and when it comes to basically your home, you can detect exactly what the water quality index is, and you be able to detect if indeed this water is fit to drink. Now, in the old days, or currently in many countries still, what we're doing is when somebody drinks contaminated water, the person becomes sick. We wonder, oh, let's check the water out. And the water is sent for testing, and normally takes about 48 hours for the results to come back. With this monitoring technique, it's instantaneously, you would know whether the water you're about to drink is safe or not because you have a water quality index, which is detected by a sensor in the platform itself. So what we now want to do is to bring some of those technologies into construction. The first one I want to talk about is operational monitoring. So as I said, there's 28% of your carbon emission, which is actually coming from your services, which is heating, lighting, repairs, maintenance, those kinds of things. And that's actually in the operational phase is very, very large value. So you can see that there is a large amount of carbon which is emitted through the operational phase itself. And what we have faced as challenged, I think, in this building. So if you look at this particular building, there's of course a system operating behind all the services that it's providing. But we do have issues now. It's if you wanted to maximize your efficiency or minimize the carbon emission from this particular building, we have a lack of real-time energy monitoring, and that could be done easily. I think, and then I'll talk about the sensors for that. Need for granular data, component level and room level, sensor integration. So you get in these sensors which can be completely integrated for all kinds of different things now. Energy and comfort simulation. So you want to be comfortable, but I think your comfort is then connected to your services and it's indeed connected to your indoor environment, which means that if you integrate all this, you could actually come up with much better algorithms which can control the energy this particular building is consuming. And then, of course, you can bring AI models. Now, there is a lot of commercial sensors out there right now. So there is commercial sensors for HVAC operations tracking, environmental comfort, occupant uses and deflection, and communications and integration. But only problem is these particular sensors are not integrated, which means that they all operate individually. So some of the work we're doing at UBC is to integrate these sensors as to how they would work. So our mission is to minimize carbon emissions with improved occupational comfort. This is some work that we're doing with Professor Tony Yang. Develop a low-cost, real-time, edge-computable kit set for indoor environmental quality and building energy monitoring. Design the state-of-the-art algorithms for optimal sensor deployment, data interpolation for global reconstruction. And then you have the structured data management that uses ontology and GNNs, which is graph neural networks, creating a digital twin for the building, which can then be optimizing and minimizing the total carbon emissions from this. So there are three components to this. There is the HVAC operations, which is sensor, which is a specific purpose it has. So you can monitor temperature, airflow, differential pressures, current transformer clamps, and the wall position sensors. This is sort of one area which is now controllable. You have the occupant and usage detection. So once you are in the room, the building should know, A, how many people are in this particular room, who is moving, what the movement is like, etc. So you have the motion sensors, cameras, and smart plug, which is power monitoring. And then finally, something that we really care about is the indoor air quality. So this indoor air quality can be actually in terms of air temperature, mean radiant temperature, velocities, CO2 concentrations, and the light level, basically. So that all combines into indoor air quality. Now, I can control this part, and these two parts become the feedback. So you have the occupant and usage detection becomes the feedback. Your indoor environment quality becomes the feedback. And what you're doing is you're feeding this back into the system, which is controlling your HVAC operation in order to maximize comfort and minimize the carbon emissions. So you're not wasting any energy per se. So here is a building that we have at UBC called the SIRS building, and this has got sort of these integrated sensors. So you basically have on the indoor quality, there's the indoor quality sensors that I just talked about. You have the occupant and usage detection in the building itself. They're each feeding the data over to a single board computer, Raspberry Pi type program. And then what it does is it actually controls your HVAC sensors in order to maximize the quality of indoor environment and maximize the usage or your occupant comfort. So in a closed loop format, what you could do is you can run this thing on any building through sensors, which will allow you to minimize carbon emissions, minimize the energy requirement, and also at the same time maximize occupational comfort and indoor air quality. In the end, what we're doing is creating a digital twin for basically BIM or building energy model. So here is a physical BIM, and there's a physical BIM with the energy overlay on it. And this is, this is the way that we are doing at this source building is to essentially minimize the energy requirements. And again, this is creating a digital twin from the sensors that are providing you with the data, and that will allow you to basically minimize the energy requirement in the sensor itself. So that's on the operational side. This is a very active functioning, I would say, set that we already are working with, which can be adopted in any building, anywhere else in the world as well. So we could certainly look at how we could be putting sensors in a specific structure and minimize the energy requirement and, of course, to minimize the carbon emission as well. The next I want to talk about is structural health monitoring, safety, and carbon reduction. And I really believe that again, coming from safety and resilience, this is something that we all need to sort of look at how we monitor safety. So I'm not talking about serviceability. I'm talking about the safety in a structure along with resilience. So in the old days, we used to do, and this is still being done, is to do global damage detection. So you have a building, for example, and I'll show you a building in Chile that we have been monitoring along with Professor Carlos Ventura. So you have a building which has got sensors on it. So these sensors are generally accelerometers, which will actually detect the natural frequencies of the building. And when you do this, you have this particular building that we were monitoring using the ambient vibrations. This is a building, it's a 9-story building in Chile. So we had about 65 accelerometers on this particular structure. And we were monitoring basically the natural frequencies of the structure itself. Now, this monitoring started back in 2007, and what happened was in 2010, there was an earthquake. And clearly, immediately what you could see is that's the drop in the natural frequencies. Now, it meant clearly that because there's a drop in natural frequencies, there was damage in the structure itself. And of course, you can see the sort of the seismic event per se there, but you can see also the daily ambient vibrations and changes in the structure itself. But what this told us was that particular earthquake that occurred in 2010, it changed the natural frequencies of the structure and it dropped the natural frequencies. So there is a damage there, but what you don't know is where the damage is, because this is just giving you a global picture in terms of where the damage is, but you don't know where the damage is, for which you require topical sensors. The topical sensors are the sensors that are placed at specific locations, which will allow us to actually detect where the exact damage is. So I want to introduce some new sensors that have been developed that we are particularly working with. So these are more topical sensors. So I can place more of these in the structure, and these will be able to tell us exactly where that exact damage is that we just detected through this drop in the natural frequencies, for example. So there's a whole bunch of sensors. There's the pressure transducers, fiber optic sensors, tilt beam sensors. There's a whole series of them that are available now, which needs to be integrated into the structure for safety assessment. It's a simple thing. You can either use so you get this data from these sensors, which is actually analog data. And this you have a microcontroller, which can actually convert the data into digital signals. You can send the digital signal to a cloud platform. And what we're doing this, we're using generally is different type of a network, like the Larawan network or some similar network, which is actually long range wide area network, which is it's sort of infrequent data. Sometimes you don't require the data over every second, for example, so it can detect data over a time period that you want this data to be acquired, and it actually then sends it to the cloud where you can start actually working with the analysis. So I want to describe some of the structures we are monitoring now in Canada with using a similar network, and I'll tell you exactly why we are monitoring these structures. So that's Canada. I am from Vancouver, right here on the West Coast. And I'll describe one of the bridges that we're monitoring is this particular bridge called Safe Bridge. But also I'll describe this particular monument that we're monitoring, which is the Golden Boy. And one other bridge that we're monitoring is the Prince Edward Island and Newfoundland Bridge, which is the Confederation Bridge, we call it. And one other structure I want to describe is basically the Gentilly nuclear station, which has got a lot of it's a decommissioned nuclear station, which has actually got a lot of spent fuel inside. So the first one, which taught us a lot, was the Confederation Bridge. This Confederation Bridge is a 14-kilometer long bridge. And in this particular bridge, when this was being designed, the designer thought that because it's all a frozen water, you would have these ice sheets that are floating in the water, and that would actually go and impact on the pier. And of course, the designer thought that would become the critical condition because these forces are extremely large. So we put a lot of sensors on this structure. So this is particularly between Pier 33 and P33, Pier 33 and 30. There's a whole bunch of sensors at Pier 34, which actually measure the impact which is coming from the floating ice. And of course, it has got 500 strain measuring devices, 450 thermal sensors, 76 accelerometers, 6 dynamic tilt meters, displacement transducers, ice load panels. That's the one I just described up here, and underwater sonar systems and 4 time-lapse video cameras and laser system. So when you have all this instrumentation, you're collecting the data, enormous amount of data from the bridge, which is allowing you to basically understand how is the bridge being, after the construction, how it's performing. Now, of course, the designer was very concerned about the ice forces, whatever the ice forces would be on the specific pier. So we put these sensors here, and it turns out that those ice forces were not very large at all. Although the designer had actually designed for very high ice forces, this were not very high, which actually tells you that the sensors can be very useful for design, which means that now the next structure that you're designing for those conditions, you would know much better what should be the critical condition of design as opposed to this assumption that we make. For example, in this particular building, we are probably using up to 20 to 30% more material because our loads are extremely unknown. They're not very, there's an uncertainty in terms of loads that we have in this structure. That's why we keep providing a very large factor of safety. If you had sensors, you would be able to actually know exactly what the loads are on a structure of this type, which means that you can tighten the designs enormously. Next, I want to very briefly describe this Gentilly nuclear station. This is just outside of Montreal, and it has got spent fuel inside. So it's got radioactive fuel inside. And this one was retrofitted, that ring beam that you see up there, that was actually built, and it's got a lot of sensors in it. And this was the one to keep the entire structure intact so that this fuel, radioactive fuel, which is inside, would not escape. So we have a lot of sensors in this particular structure, which will allow you to make sure that this radioactivity should not escape, basically. And we have also placed some radioactive sensors there so they can detect if there is any radioactivity that's actually leaking from the system itself. And so far, I think we don't have any problem of that particular nature. Now, I want to describe a very beautiful structure in Canada, which is called the Golden Boy. So Golden Boy is a 5-meter tall structure, very large structure, very beautiful. And it's on the Manitoba Parliament. It's in the Parliament, which is in the city of Winnipeg, which is sort of right in the central Canada. And this one, the statue, they made a mistake. It was not designed to include the light above the torch. So they had actually not designed to carry the torch. And so they had to actually drill through and put this torch up. And when they put this torch up, they damaged the statue. And as the statue got damaged, what happened was water leaked in, seeped in, and a lot of other elements seeped in, and the particular shaft on which this particular statue is standing started to get corroded. So, of course, a couple of years back, we went there, we removed the statue, we put a new fiber-reinforced polymer shaft in the middle, and then we also put sensors. So when we did put sensors, particularly accelerometers, when we detected that there was a corroded shaft, the thing was vibrating at about 1.5 hertz. And when we did the analysis, it seemed like the statue, its first natural frequency should be about 3 hertz. Once we put the new shaft in, we did that same measurement again, and sure enough, we noticed that the frequency had gone up to 3 hertz now, which meant that we were able to restore this statue to its previous condition through a repair. So you can see how sensing can become very useful in also assessing whether the repair that you have just performed on the structure is adequate or not. So last structure I want to describe is the SAFE bridge, which is a shear deficient bridge. And what we did was we strengthened it with sprayed FRP. So here is the sprayed FRP that we developed, which we strengthened this particular bridge, the girders that needed this shear deficient system. So we strengthened it with sprayed FRP. And then what we did was we put sensors on the inside. This is on the rebar. And there is these long gauge fiber optic sensors, which we put across the entire length. So these long gauge sensors, this is a 7-meter long girder. So we could actually measure the overall strains over the entire length of the girder. And in the end, what we were able to do was to basically see that indeed, as a result of our new retrofit, we were able to increase its shear capacity. And the two sensors were able to tell us if the sprayed FRP was debonding. So if you have the strains which are compatible between the two systems, we would know that the layer that we have placed is actually not debonding. So it's a very useful way to understand what's going on. There's some sensors we are using on construction load monitoring. There was a structure that collapsed in Kolkata in 2015. This was under construction because the scaffold gave in. So the scaffold actually collapsed, and we have these sensors which cost about $1. And there's no particular reason to sort of lose lives over $1 worth of sensors. So I think we are putting a lot of these sensors on scaffolds now, which can control basically what we actually see in this structure. Now, the next series of sensors I want to describe are cement-based sensors, what we call piezoresistivity. So this is smart concrete. So you have concrete, what we can do is we can make it conducting. And the moment you make it conducting, either through carbon nanotubes or through carbon fibers, what happens is this becomes a sensor. And here, are the results from a specific sensor. So this is smart material now, which can be used as a sensor. You could just flood this building with this kind of sensor because it's very cheap. You can just make the structures much smarter just by using some kind of a conductive element. And you can see here is that these sensors actually are, this is my fractional change in resistance. This is actually the data which is coming, a signal that's coming from the sensor itself. And this is the actual load that is being borne by the element. And you can see that by simply the sensors actually completely mimic what the load is on the structure. So I don't need to measure the load. What I can simply measure is the signal. And I think that really works extremely well. So these are some piezoresistive sensors that are being monitored and into a structure, and I'll describe this again later on. We're using some of these sensors for roads, particularly if you're trying a new technology. So this has got some of those sensors in there. And again, we embedded these things in this Nemkumar bridge. And you can immediately see that some of the technologies that we were using, for example, modified tire fiber here, what we were noticing is that this particular system, this modified tire fiber system, was giving us actually lower strains and indicating an enhanced rutting resistance with this particular fiber. So the idea I'm trying to say is that you can use these sensors to essentially evaluate a new technology and also monitor at the same time as to what the strains in this particular system are. Last thing I want to detect or talk about is the resilience monitoring and disaster prevention. So for resilience, what you really want to do is to do chemical monitoring. You want to understand how the chemicals are moving in the system. So as you know, corrosion will be caused basically by chlorides, which will get into the system. You exceed a certain chloride threshold, and you can now start to see the corrosion. Now, every time we detect corrosion is generally very late because you detect the corrosion when you already see some staining on the structure. Here, if you have a sensor which can detect the chloride profile, I will know years before corrosion will start that the corrosion is now starting because of the threshold of chloride has been exceeded. So this particular sensor that we're using, which is for chemoresistivity, we call it, what we have is you can detect chloride profiles, sulfate profiles, water ingress, and corrosion. And in particular, what we're using is this chloride doped polyaniline, PANI, with carbon fibers. And what it shows is that the moment I have the sensor, I can detect what the actual amount of chloride at that location is. So it's topical sensing, basically. And here is, in fact, you can see that the R square that I have with respect to concentration and my signal is extremely good, which means that I can detect exactly what the level of chlorides is at any location in the structure, which will allow me to detect how far am I from actual start of the corrosion. Now, the same sensor, which is a chemosensor, can detect also oil. What that means is I can use this particular sensor now to detect leakage in pipelines. So if you look at this particular pipeline, which is leaking here, I can have a smart patch, which is essentially a chemoresistor, and it can tell me as soon as there is a leakage in the pipeline, it will give me a signal. And it's very useful because, in an oil exporting country like Canada, we have a ton of pipelines there. So it's a great way to actually detect. And of course, you will notice our prime minister here our former prime minister, I should say, who came to see our leak detection system. And it's actually been applied into number of pipelines now, actually. The other sensor is what we call for disaster prevention is with medium recognition. Now, medium recognition is a very smart thing to do because if you're trying to monitor certain things that are going on in the structure. So medium recognition could be done through beam photoelectric sensor, diffusive reflective, surface capacitance. So there's a number of these sensors that are available that detect the medium. The medium is the medium which is between these two probes. And that becomes a very useful way of detecting a number of things. So for example, what we're doing is we're detecting, for example, or using these sensors for scour. Now, scour is a very big problem, which is part of our coastal protection. In British Columbia, and I'm sure the numbers here are very similar, in British Columbia, 60% of the bridges are showing scour. Scour is where you start losing the foundation. And remember that Minnesota bridge collapse that occurred some 20 years back? It was all because of scour, because the foundations tilted and the whole structure came down. In British Columbia in 2020, on one highway, 6 bridges collapsed because of scour. 6 bridges collapsed because of scour. The scour is when you lose the foundation. And with climate change, because the water flows are becoming larger and larger, you have a lot more problem with scour in our bridges now. As I said, 60% of bridges in British Columbia are showing a scour. So all of a sudden you have this problem of scour. How do we deal with it now? You sort of go down, you send these divers down there, and it's murky water. They can't even see how to take pictures inside to detect if the foundation is actually lost or foundation is scoured. But these sensors are the best, actually. So I can place these sensors right where the foundation is. And what I will notice is basically the following. Here's a typical sensor, which is based on the through beam photoelectric sensing. Here's a typical sensor, which is going down to the foundation level. So you can see if I can place it vertically at the foundation, this top sensor is in water. We keep it in the water, and the other sensors are actually in the foundation, embedded in the foundation. Now, of course, if I look at the signal here, you can see that the top sensor, which is always in water, is giving me a straight line. But the moment the scour occurs, you can notice that the one which was embedded, as soon as you start losing the foundation, you will start basically having that sensor detect that it's now not in soil, it's actually in water, which means that the water level is dropping down and the foundation is being lost. So immediately I can tell that all of a sudden, and this would be the second sensor, this would be the sort of the third one here, that starts as soon as the scour takes place, it's sort of starting to give me a signal as well. Imagine how powerful that is now in terms of really being able to detect scour, because I don't need to send a diver down there. The divers are not needed. I can get a signal immediately from the scour sensing itself. So we are monitoring this in number of structures now. There's a typical sensor, which is actually monitoring scour in the structure itself, and you are able to do this. And I believe this could be a wonderful sensor for detecting floods. So remember that the Daiichi nuclear power plant in Fukushima, where the basement got flooded. And as the basement got flooded, there was a meltdown basically in that particular nuclear reactor right after an earthquake. But if you had a sensor which can detect medium, you can detect that the basement is now flooded, which means that you would actually turn off the operations much before you would detect, what's going on. So you can do, this is exactly what we can do with these systems. You can detect mudslides. So these mudslides, if you had a sensor, would be able to tell you that the mudslide is about to occur because it will measure the shear strength of soil in between those two probes. And you can see that now you can start detecting mudslides. You can detect the shrink well. This is a Winnipeg building that has got this kind of, and you can be detected very easily. We are using this to detect what we call a scour or washout of railway tracks in India. Here's a typical railway track that has had a washout. And, of course, this is an accident waiting to happen. This is another one in Kenora as a result of washout of the tracks itself. But any medium recognition sensor can actually tell you that it is actually going to be, quite effective in that particular sense. So the last thing I want to talk about is biological sensing. And the people from the water side actually guided me to understand how to detect biological DNA. And why am I interested in this? Because we have a major problem with biological attack, what we call microbially induced corrosion in our sewer pipes. Just under your feet, these sewer pipes are completely deteriorating because of a bacterial attack. The suspect bacteria is called Theobacillus. What this bacteria does, it converts hydrogen sulfide into sulfuric acid, and that sulfuric acid would actually allow you to corrode concrete. And it's a massive issue, massive, massive issue. Millions of kilometers of sewerage is rotting because of this particular attack. So what we are doing is we are detecting the DNA of this particular microbe, which is Theobacillus, through some kind of a microgel-based optical sensor. So you see the peak shift, and that peak shift is completely related to the type of DNA protein that we are actually detecting. So imagine you have a sewer which has got the creation of a Theobacillus type bacteria. I have a sensor which can detect that that particular biofilm is being formed, and the moment that biofilm is formed, what I can do is I can create a system whereby it's a closed loop system with a crawler which can go inside the sewer, detect where exactly that biofilm is being formed, where that bacteria is active, and spray a specific biocide. And this closed loop system is, I believe, the strength now that we can sense things. We can basically produce a system whereby you're only providing biocide where it is actually needed, as opposed to this willy-nilly biocide sprays that we put on a lot of structures itself, actually. So that comes me to the end of my talk. What we're really doing is that we want these sensors to be integrated into a structure and create basically some kind of an app which can then monitor every structure, not just for its service carbon comfort, but also for its structural safety and resilience. And I believe it's all possible with the right amount of sensing that we can do. Create a digital twin which will help us allow the use of AI into basically managing the structure as we go forward. And in the end, this is my dream. I think in the end, when you're talking about smart city, a smart city is where all services are integrated. You're not dealing with transportation separately from sanitation. You're not dealing with sanitation separately from energy. And they're all integrated through sensors. And in the end, what you have is a control module here, which can monitor entirely the operations. And in the end, what you could do is you can minimize basically the overall carbon that you are actually going to release. My concluding remarks. So digital infrastructure with IoT-enabled sensors is the future. Such infrastructure smartness enables minimized lifecycle costs, prudent asset management, and in the end, carbon neutrality, which is all we are aiming for. And significant data are needed for machine learning AI to become useful. So put more sensors in these structures so that we can create those AI algorithms that we require. Thank you.
Thank you, Professor Banthia, for this very, interesting and also advanced technology in sensing of infrastructures. Thank you. So could you have a seat over there, and then maybe we can have some Q&A? Yeah. Any questions from the floor, from the audience? You can use the mic in front of you. Just press. Yeah, please.
Hello, Professor Banthia. Thank you for your impressive presentation. I have a question about the sensor structure health monitoring. Actually, recently there are lots of work by adding some nanomaterials such as nanoblack or nanocells to improve the stress sensor performance of the concrete. So I want to ask you about your opinion on these technologies and what's the challenge of this technology for theory used in the structural health monitoring. Thank you.
All right, thank you. That's a very good question. So we are using quite of these nanomaterials in developing smart concrete now, of course. So the idea is to improve its impedance or conductivity, and then it becomes a sensor. So a lot of carbon nanotubes, a lot of graphene, we're using a lot of these materials in order to build sensors which are smart, and they give you a very good signal, basically. So higher the conductivity, better is the signal. So if you look at the gauge factors that we are noticing in these things, these gauge factors are in fact almost 2 orders of magnitude better than your traditional sensors. So it's a very, very sensitive sensor that we can create through these nanomaterials, basically. What is a challenge in integrating them? Cost is one, clearly. Cost is an issue. Connectivity is an issue. Power is an issue. But I think if it's in an urban environment, these problems are not a problem. You can deal with power, you can deal with connectivity and things like that. It's in the remote areas it becomes a problem because you may not actually have the signal there. You may have to sort of generate power through some solar power or whatever, and connectivity can become an issue as well. So yeah, those would be the issues.
Thank you. Other questions? Yes, please, Mr. Zhang.
Thank you very much, Professor Banthia. Very eye-opening. So I do have two questions. The first one is about the severity. I remember you have a slide saying that the frequency of a building changed after the seismic event. But how can we correlate the severity of the damage with the frequency? How do we know where or when is the time that we need to have some fixation measurements take place? That's my first question. How we correlate the severity damage to the frequency in real buildings, for example.
Sure. So if you have a dynamic model, I would be able to tell you, how severe the damage is because you know exactly what the natural frequency for second, third, fourth, fifth frequencies of the pristine structure are. And if I now have a depletion in that frequency, I know how far am I from an actual structure. However, it's very challenging, as I said, because you don't know, first of all, how severe the damage is and where the damage is, because it may be a global number I'm looking at, but that global number means, the example that people give is that I have my one hand at 30 degrees and one hand at 10 degrees water. The average is pretty good, right? So the thing here is that you're looking at a global damage, but you don't know how severe the local damage may be. And that's where I think you need to be careful and you need to sort of do some further analysis with topical sensing, for example.
Okay. Thank you. And my second question is about, I do have some experience on optical fiber. Like we try to use optical fiber on 3D printed concrete. So we try to measure the continuous shrinkage. One of the issue I encountered before is that the optical fibers are very fragile. Do you think that's going to be an issue when we implement sensors? They can be break very easily. Do you think that's an issue to complicate the entire, like for example, concrete production process?
So there's many types of optical fibers that have very, very robust coating.
Robust,
of them.
okay.
Yeah,
okay,
there's quite a few of them.
Okay.
But are you actually putting sensors while printing? So it's in the concrete?
Yes, within the interlayers. We design a system while we're printing, while the optic fiber can be, continuously embedded, so we can measure the continuous shrinkage at early age.
Yeah.
But we had this challenge of, make it properly embedded in without breaking it.
I would use piezoresistive sensors there because we're using some of them because they're much easier to embed. And also the concrete doesn't see them as a foreign element because they're made with cements, so they bond very well and they can give you a lot more information because
more compatible.
More compatible every possible way. So I would actually embed some piezoresistive sensors there.
Okay, perfect. Thank you very much.
Thank you. Other questions, please? I have a question, Nemi. We are very much into the low carbon concrete area now. Okay, we are trying to reduce cement content and also improve the durability as well using a lot of low carbon SCM, supplementary cementitious material, right? And then with that, we lower the pH of the concrete, right? And then there will also, of course, it would improve the durability for chloride resistance, right? We all know that. But they will also have lower the pH and then high risk of carbonation-induced corrosion, right? There is the controversy now in the concrete industry whether how much SCM we put into it in order to balance the benefit and corrosion risk. So how can sensor help with this solving this issues? Of course, we can put a pH sensor in here, right? But does the pH tell us everything about a low carbon clinker? Do you think it's just as simple as that, or do you think there's more than that?
That's a very good question. No, it's more than that, obviously.
Yeah.
Like, and I personally believe that, I mean, even with, there's some of the data that we have with respect to even high volume fly ash, for example, people did believe that. I think you're somehow reducing the passivation on the steel surface.
Yes.
But somehow that didn't play out, at least in real life, that you would still have sort of pH of say 11 or 12, even after, adding huge amount of, supplemented cementing materials there. So it didn't actually pan out it was not as doomsday as people thought that it would be.
Mm-hmm.
However, I think what I would recommend is, in fact, some of these chemosensors.
Chemosensors.
Yeah. See, chemosensors would be able to tell you a lot more.
So what sort of iron species can it really measure as accurate as we monitor corrosion? So what sort of iron is specifically in mind for chemosensors?
So what we're doing is, so it will change its impedance based on any chemical intrusion. Only thing is, it will also change impedance based on sulfates as much as it will change impedance based on chlorides.
Mm-hmm.
This is where we do spectroscopy.
Mm-hmm.
So if you're monitoring basically the signals and do a fast Fourier transform on it, then you can detect which particular peak at what frequency is related to a specific ion.
Mm-hmm.
So you can detect if indeed, and in this particular case, we know exactly where that frequency is with respect to chloride. So if that's really the one.
Yeah, chloride is, I think, is
it's easy to
well
do.
known.
Yeah,
but sulfate or sulfide, other species, I don't know whether it's already well established though.
We can detect them. We can detect those as well. But in this particular case, there's no need to detect them because chlorides are the ones that are going to cause the corrosion in the long run, actually. So and we can detect them easily with these chemosensors. So it can not only detect the presence of it, it will also detect the concentration of it, which means that if you knew, what the threshold is required for corrosion, I will be able to tell you long time back that you are safe 6 years away from corrosion to start now. And then you can assess this with respect to your SCM addition and see whether it's working or not. So, yeah.
Okay, thank you. More, please. Yes, Frank.
Thanks, Professor, for your wonderful presentation about the sensor, which shows to be a very powerful tool. So maybe another powerful tool is the AI, especially under the development of the large language model. So my question is, how do you think the AI will influence the research of the civil engineering and the construction materials? So what's the opportunity, the challenge, and the currently the problem in this related research? And as the chief editor of the CCC, do you prefer this related research? Thanks.
Looks like you have a paper coming up soon.
No. Actually,
I know, I'm just joking. I'm just joking. Of course, I see a huge role of AI here. But AI to me is a tool. And if you have that tool, if you can use it properly, first of all, if you have sufficient data, you can actually generate a lot more guidance, I think, on materials design, on infrastructure management, when to apply the repair and that sort of thing, which can be very useful, actually. So, for example, we're using quite a bit of AI in terms of controlling the serviceability side of the structure, which is quite a large carbon sink, So your HVAC can be controlled very well through known algorithms on known existing data. We understand really so AI understands, for example, what the occupational comfort is. You don't need to reinvent that wheel. We understand what humans like, for example, right? We understand really how to control movements. through AI, you can do that, which means that when you take these data, you can come up with sort of control or feedback control loops onto your HVAC system, which will allow you to minimize the carbon, right? So I believe in the broader sense, more data we collect, more data we have, I think your AI model will become more powerful and more robust and more reliable, right? At the moment, we don't have a lot of data. So, listen, ChatGPT will never say, I don't know, right? It will give you always a response, but sometimes that response can be extremely narrow and inaccurate sometimes because there's not enough data, So as more data we generate, I think AI can become a very powerful tool in infrastructure management.
Yes, thanks. So how do you define the time, whether we already have enough data or already not?
When my results look good, when I'm able to actually see the influence on carbon emissions, right? I don't care about whether it's a good data or good AI model or bad AI model. My objectives are very clear. I want to reduce the carbon emissions from a building. And if the AI model is able to help me do that, then that's a good AI model for me because it's meeting my objectives, right?
Okay, thank you.
Any further questions? Now you mentioned, Nami, you mentioned you're using a sensor to monitor the scaffolding, right? That is very important in Hong Kong, I think now. Now we have debate, or not debate, I mean there's some discussion of because Hong Kong use a lot of not timber, I mean this bamboo scaffolding, right? And of course there's some issue with the bamboo scaffolding and versus what you have been using in Canada is steel scaffolding, right? So do you think the sensor, because in order to promote the safety of using bamboo, maybe can this sensor be used with the bamboo scaffolding, and what's the challenges of, bamboo have its advantage, but of course there are some disadvantages, right? So what's your view?
That's a very good question. I have not thought of that, but I think these sensors can be attached to any surface.
Yeah.
And if you truly knew what the ultimate capacity of bamboo is, my sensor will be able to tell you how far are you from that ultimate capacity, which means if you keep a certain factor.
But there's other issues, right? There are wind load and there are, I don't know, the workmanship. And so it's not so simple as a steel scaffold, right?
Yeah, I'll have to think.
The analysis of bamboo scaffolding is an art as well as a science, I think. Yeah.
Well, there's a research project right there for you. We can see if those sensors actually work.
Yeah.
In terms of detecting collapse in a bamboo scaffold, I think it shouldn't be very difficult.
This could be very interesting.
Yeah. Exactly.
Research topic.
Sure.
I don't know, Professor Wang is here. Professor Wang, he's not here. Okay. There's one final question because I'm speaking on behalf of, I spot there are many young researchers in this room. And you are the chief editor of CCC, Cement and Concrete Composite. It's the most prestigious journal in the concrete area, okay, at least. So could I ask on behalf of them, how can we get our paper accepted? By you. So what's the trick? I mean, there are many desk rejection now. I understand. As I'm also on the editorial board, I desk reject quite a lot. So can you please also advise our young researcher, how can they avoid being desk rejected and get through the process, okay, more smoothly?
Put Professor Poon as a co-author. We never desk reject his papers. And that's No, but I think it's good. At the end of the day, I think, we get about 4,000 papers now, and it's just a sheer volume issue. So sometimes we either see duplication of work, sometimes we see overlap with previous work, sometimes we see lack of innovation. Sometimes we just see that it doesn't fit the scope, So CCC is not a chemistry journal. There are chemistry journals out there like CCR and all. We are more towards engineering properties. So engineering properties that can be used by a designer, for example, or can help us develop specifications for a material. So when you're doing work which is highly fundamental, we want you to tell us, how does that relate to real life? It's very important for you to connect that to engineering properties. So make sure that, when you're putting in a fundamental paper, you also give it a thought. I mean, some of the discussion that we had yesterday, for example, I think it's important for you to understand as a researcher, as a PhD student, what are the greater implications of your work are in the context of design, context of engineering properties, context of durability. And if you do that, it does two things. It connects you to the scope of the journal, first and foremost, because we are looking for that kind of work. And secondly, you will be surprised that will probably also give you further ideas about your own research, because you will then bridge that gap between what you're doing and what the real life needs, what the industry needs, right? So we are a bridge between you and the industry. Think about it that way. And if you're coming up with issues or coming up with solutions to a problem, help us understand how you're solving a specific problem. It may be very fundamental, that's fine, but we do fundamental research to solve problems, of course. So tell us how you're connecting it to real life. Did I answer it?
Yes.
Good? Okay.
Yes, please remember that. Okay. Thank you very much again, Nami. Professor Banthia. Let's give him another round of applause. We have a little souvenir for Professor Banthia.
Oh.
With that, we conclude this seminar, and on behalf of the university and pair, we thank Professor Banthia once again. Thank you. Thank you very much for coming. Thank you.